Today we are going to learn about mastering PyTorch Autograd for complex backpropagation, focusing on implementing backpropagation with custom and multi-layered neural networks using Autograd.
Welcome to our video on mastering PyTorch Autograd for complex backpropagation tasks. In deep learning, understanding how to efficiently implement backpropagation is crucial for optimizing neural networks. PyTorch's Autograd is a powerful tool that allows for automatic differentiation, making this process much easier. Today, we'll explore how Autograd works, its role in backpropagation, and how to implement it in custom and multi-layered networks. This knowledge will equip you with the skills needed to manage complex neural network tasks efficiently.
Backpropagation is a fundamental concept in training neural networks, involving the calculation of gradients to optimize model parameters. Traditionally, this process can be cumbersome and error-prone when done manually. This is where PyTorch's Autograd comes into play. Autograd automatically computes gradients, making the differentiation process seamless and efficient. It tracks operations on tensors to create a computation graph, which is then used to backpropagate errors and compute gradients. This automation not only saves time but also reduces the likelihood of human error, allowing researchers and developers to focus on designing and refining models instead of getting bogged down by the intricate details of gradient computation. Let's start by setting up a simple neural network in PyTorch. At its core, a neural network consists of layers of nodes, or neurons, where data is processed. In PyTorch, we define these layers using the nn.module class. For our demonstration, we will create a simple feed-forward network with an input layer, one hidden layer, and an output layer. We'll use Autograd's capabilities to track gradients automatically. By applying sample data, we can observe how the network processes inputs and generates outputs. This foundational understanding is crucial before moving on to more complex architectures. We will also discuss how PyTorch's flexible framework allows us to customize and experiment with different network configurations easily.
Autograd not only simplifies automatic differentiation but also provides the flexibility to customize gradient computation. This is particularly useful when you want to implement non-standard operations in your neural network. Using torch.autograd.Function, you can define your own forward and backward passes. The forward pass computes the output, while the backward pass computes the gradient of the output with respect to the input. This customization allows you to fine-tune how gradients are calculated, enabling more complex operations and optimizations. We'll explore some practical examples to illustrate how custom gradients can be implemented, providing you with the tools to extend Autograd's capabilities to suit your specific needs.
As neural networks become more complex, with multiple layers and connections, managing them efficiently becomes crucial. PyTorch's Autograd is invaluable in these scenarios, as it handles the intricacies of gradient computation across layers. When dealing with multi-layered networks, it's important to manage the connections and data flow between layers effectively. Autograd streamlines this process by maintaining a dynamic computation graph, allowing gradients to be computed efficiently, regardless of the network's depth. We'll examine a case study of a multi-layer network, showcasing how Autograd facilitates seamless backpropagation across various layers, ultimately leading to improved network performance and training efficiency. Efficient memory management is essential when training neural networks, especially with large datasets and complex architectures. PyTorch provides several techniques to optimize memory usage during backpropagation. One strategy is to use checkpointing, where intermediate results are recomputed during the backward pass rather than stored, reducing memory footprint. Another approach is to profile memory usage using PyTorch's built-in tools to identify and address memory bottlenecks. By understanding how memory is allocated and utilized, you can make informed decisions to optimize memory without compromising model performance. We'll explore these techniques in detail, providing practical insights into managing memory effectively during backpropagation.
While PyTorch's Autograd simplifies gradient computation, errors can still occur, especially in complex networks. Common errors include incorrect tensor shapes, NA-NS and gradients, and runtime errors during backpropagation. Identifying and addressing these issues is key to maintaining a robust model. We'll discuss debugging techniques, such as checking tensor shapes and sizes, inspecting gradient values, and using error messages to pinpoint the source of the problem. Additionally, we'll share best practices for error resolution, emphasizing the importance of learning from debugging to prevent similar issues in the future. By the end of this section, you'll be equipped with the skills to troubleshoot and resolve common Autograd errors efficiently.
Debugging backpropagation issues requires a systematic approach to ensure efficient and effective resolution. Start by logging and monitoring key metrics during training, such as loss and accuracy, to identify anomalies early. Visualization tools, like TensorBoard, can provide insights into the training process, helping to pinpoint where issues may arise. Testing and validation strategies, including cross-validation and regularization techniques, can further enhance model robustness. Continuous learning and adaptation are crucial, as new challenges and complexities emerge with evolving models. By adopting these best practices, you'll be better equipped to handle backpropagation issues, ensuring a smoother and more reliable training process. PyTorch's Autograd is widely used in various real-world applications, from image processing and natural language processing, NLP, to reinforcement learning and scientific computing. In image processing, Autograd simplifies the development of convolutional neural networks, CNNs, for tasks like image classification and object detection. In NLP, it aids in building recurrent neural networks, RNNs, for tasks such as language modeling and translation. Autograd's flexibility and efficiency make it a valuable tool in reinforcement learning, where dynamic computation graphs are essential. Additionally, its applicability in scientific computing allows for complex simulations and predictions. We'll explore industry case studies to illustrate how Autograd is leveraged across different domains, highlighting its versatility and impact. For expert users, PyTorch's Autograd offers advanced techniques to further optimize and customize neural networks. These include advanced differentiation techniques, where users can implement complex operations with precision. Optimizing custom layers allows for greater control over gradient computation, enhancing model performance. Exploring hybrid models, which combine different types of neural networks, can lead to innovative solutions for complex problems. Dynamic computation graph manipulation provides flexibility in model design and execution, accommodating changing requirements during training. We'll delve into these advanced techniques, showcasing innovative use cases that demonstrate the full potential of Autograd for expert users. In conclusion, mastering PyTorch Autograd for complex backpropagation empowers you to optimize neural networks efficiently. We've covered the role of Autograd in backpropagation, setting up and managing networks, customizing gradients, and troubleshooting common errors. As deep learning evolves, staying informed about future trends in Autograd is crucial. Continuous learning and experimentation will enhance your skills and open new possibilities in neural network design and optimization. We encourage you to explore further resources and apply what you've learned to real-world problems, leveraging Autograd's capabilities to their fullest potential.